Okay, so in the last video, we verified again that pi1 stable, or at least its two component, is Zmod 2, even though we knew the whole thing was Zmod 2. And in this video, I want to push the computation a little bit further and show you kind of the flavor of how this would go if you wanted to continue. So before we push it further, let me come back and verify a claim. So last time we were looking at this map KZN to KZ mod 2 n plus 2 that we called square 2, just because square 2 iota n is a thing in the cohomology of KZN. And then over on the right, we had the loop path fibration. And so we took the pullback. It's supposed to be a +1. Okay, we took the pullback and called that x1. And that gave us a fibration with the same fiber. So KZ mod 2 n plus 1. Okay, and then we looked at this fibration and we ran the Serre spectral sequence, the cohomological Serre spectral sequence, mod 2, right? Everything was in mod 2 coefficients. We were talking about the 2 component. And the main thing that I want to come back and verify is that I claimed then that tau of iota n plus 1, the generator for the cohomology of the fiber, that transgresses to square 2 iota n, and that was really by construction. So I want to explain a little bit more what I mean about that. What I mean by that, and the by construction is really that square 2 is here, that makes this happen. But let's dig into the details a little bit. So the first thing we'll need is this Serre cohomology exact sequence. Okay, and we could have said this way back when we were talking about the Serre spectral sequence from the get-go. This is something that Serre proved using the Serre spectral sequence, but we didn't need it at the time, so let's just see how that goes now. Well, I want to start with a fibration, of course, if I want to talk about the Serre spectral sequence, and I'll call the fibration P and then the inclusion of the fiber I. So this is a fibration, and I want to assume that B is, my base is P minus 1 connected. Okay, now P is not a prime, and, or not necessarily anyway. F is, oops, that did not make sense grammatically. Okay, with B, P minus 1 connected, and F, Q minus 1 connected. Okay, and the claim is that then there's an exact sequence. And it's not short, but it's also not long in the sense of continuing forever. So I'll just say an exact sequence. What does it look like? Well, it has an end over here, 0, just because we'll be counting down if we go in that direction. But I can go from HP plus Q minus 2 of the fiber to, well, now there should be the connecting homomorphism. Oh, sorry. Maybe I should have said before I start writing this down that, of course, for a fibration, I have a long exact sequence in homotopy, right? And in a sense, the Serre spectral sequence is telling me that I don't have a long exact sequence in cohomology, but I might want one. And how do I adjust for that? And so what this Serre cohomology exact sequence is saying, actually, you do have a long exact sequence in cohomology for a little while. So it's not long, but you have an exact sequence for a while. Okay, and so that's what I'm trying to write here. So that's supposed to be my connecting homomorphism, right? This should go from the cohomology of the base to the cohomology of the total space to the cohomology of the fiber. And then connecting homomorphism connects back around. And so that tau, here's the connecting homomorphism, and that's also our transgression. Okay, and then this is P upper star and I upper star. And now notice that this was for B being P minus 1 connected and F being Q minus 1 connected, and P and Q have shown up in these indices. So in fact, this sequence terminates here. So it doesn't go on forever, but it's saying we have an exact sequence for a little while. And this isn't so surprising when you think about picturing the stereospectral sequence, right? If those things are P minus 1 connected and Q minus 1 connected, that means I've got a lot of zeros in my lower left corner in the stereospectral sequence. And so, of course, the transgression is going to connect my cohomology of the fiber to the cohomology of the base, and so on. It's not so complicated, but I won't prove it. Okay, let me say this is also natural, as the stereospectral sequence is, and that's really where this is coming from. And we're going to take n to be large. Remember, n is ideally the dimension of the sphere that we're after, and we're trying to compute stable homotopy groups, so we can just take n as large as we want. And remember that we were working in mod 2 coefficients. So I'm not going to write that here, but mod 2 coefficients everywhere. So let's look at what that looks like in our particular example. Let me scroll back up to it. I've actually got two fibrations here, so that's where the naturality is going to come into play. I'll write the long exact sequence. I really want to call it a long exact sequence. I'll write the exact sequence in cohomology for this one and the exact sequence in cohomology for this one. And I need things to be a certain amount connected, but I can just pump up that n really high, so I'm not going to worry about those things being connected enough. I'll just make sure that my indices stay low. So let's look at hn plus 1 of a point. That was the total space on our fibration on the right. Maps to hn plus 1 of the fiber. That was kz mod 2 n plus 1. Okay, and that's why I want to use m plus first cohomology, because that's where my iota m plus 1, my fundamental class, lives. Then I should have my connecting homomorphism, or my transgression, mapping to the cohomology of the base. So that's hn plus 2, I suppose, of the base, and the base on that side, the right side, was kz mod 2 n plus 2. And continues on. Okay, so scrolling back up just a little bit, that's this fibration on the right. I just wrote down the exact sequence, and notice I'm certainly in a range where I can assume things are connected enough that we're still in this exact sequence. But this ... it doesn't really go forever. You can't tell which one I'm pointing to. This ... of course, doesn't really go forever. Okay, now I want to write down the exact sequence for the other fibration. So that's got x1 in the middle and kzn, and then the same fiber. Okay, so what does that look like? Well, now my total space is x1. My fiber is the same. And then my base now is kzn. Keep wanting to write z mod n. Oh, it's tough. Okay, great. Okay, so this exact sequence is natural. And remember, I have my square 2 map. Goes from kzn to kz mod 2 n plus 2. So I get a map the other way in cohomology. And I'll still just call that square 2, but it's really like square 2 upper star, right? Maybe let's go ahead and put an upper star. I don't know if that's helpful. But okay, over here, this is the map on the fiber, and that's really the identity upper star, right? Same fiber in both places. And that comes from the pullback being nice. And then there's a map there. And now let's fill some of this stuff in. So I know that this is 0. It's just the cohomology of a point. And over here, I've got that fundamental class, iota n plus 1. And then because this was 0 and the sequence is exact, that's injective. And that's going to take me to iota n plus 2, which is the fundamental class for kz mod 2 n plus 2. Okay, and so in fact, that single z mod 2, where iota n plus 1 lives, maps isomorphically to the single z mod 2, where the fundamental class on the right lives, and that really is just saying iota n plus 1 maps to iota n plus 2. By the way, we've seen this before, so we don't need this exact sequence to tell us this. We just know that everything has to die because the total space is contractible, and so we've seen that the fundamental class goes to the fundamental class. Okay, so that was really, in a sense, an old story. But now how does that relate to our new story? Really the question is, what does the transgression do down here in our other fibration? And this iota n plus 1, well, it maps via identity upper star to iota n plus 1. And then the question is really, what does that map to? Well, this square has to commute, so it maps to whatever iota n plus 2 maps to, but this square 2 upper star, it's exactly named because it's the thing that maps to square 2 iota n, right? That's what square 2 upper star did. That's how we named it. It was the thing that sent the generator to square 2 iota n. And so in fact, our transgression does send iota n plus 1 to square 2 iota n, as we claimed. Okay, so that's just a good check to do. So yes, in that spectral sequence, we did have this transgression sending iota n plus 1 to square 2 iota n, and it's really by construction in the sense that we'll do this construction, this sort of construction again, and the same argument will hold there too. Okay, so that checks out the claim, but now what are we trying to do? We're trying to compute stable homotopy groups of spheres, or at least their two components. And we know pi 1 stable, but we want to push the computation further. So in order to do that, we really need to push the computation of the cohomology of x1 further in this Serre spectral sequence. So we'll do that in just a moment, but let me remind you of some ADEM relations that we'll need handy. So we've got some ADEM relations. I guess we already used in the last video that square 1, square 2 was square 3. I feel like if there's any ADEM relation you should know, it's that one. So I was kind of assuming that you did, but it's been a while since we thought about the squares. So feel free to check that one if you're not sure. Then we've also got square 2, square 2. It's apparently very hard to write squa. Okay, square 2 is ADEMable, and it gives you out square 3, square 1. Square 2, square 3, that's going to end up giving you square 5 plus square 4, square 1. Square 3, square 2, on the other hand, if you swap the order of those, then that'll give you 0. And yeah, let me just say, you can check that one. Okay, and then square 3, square 3 is square 5, square 1. I'm not even sure if we'll need that one, but maybe it's good to know. Okay, etc. There are lots of ADEM relations, but these are the ones that we'll use. Okay, so we're going to push this computation for the Serre spectral sequence a little bit further, where we're looking at this fibration where x1 is the total space, our base is kzn, and our fiber is kz mod 2 n plus 1. And we'll do all of this in mod 2 coefficients. Okay, so some of this should look familiar because we got it started last time. I wonder if I can leave those on the page and still write this. We'll see. Okay, so the base, I'm going to want to write that even lower. The base is our KZN, so that's what goes along the bottom here. And the fiber was our KZ mod 2 n plus 1. Okay, and again, everything in mod 2 coefficients, just not writing that down. And this should cook up the cohomology of x1. Okay, and this is, I scrolled back up, but this is, maybe I should have just written it again here for this fibration. Okay, which came from pulling back. That's that map square 2. All right, so let's go ahead and fill this in. All right, maybe I'll at least scroll off square 1, square 2 so that I can rest my hand somewhere. So over here in 0, 0, of course we've got 1. And then we get nothing for a while until we get to iota n. And then remember there was a 0 there. So remember our cohomology of KZN looks like polynomial in square I on our fundamental class iota n. And that I is admissible sequences with excess less than n, but not ending in square 1. So square 1 iota n is 0. Maybe it's worth writing that down. Okay, so that's why I've got a 0 here. But then in degree n plus 2, I've got that square 2 iota n. And in degree n plus 3, I'll have square 3 iota n. And remember, we said, oh, well, there should also be an admissible sequence that looks like square 2, square 1, but square 1 on iota n is 0, so that's just 0. In degree n plus 4, I've got square 4 iota n, and I guess I've also got square 3, square 1, but oh yeah, that ends in 1. I've got square 2, square 2. Oh, that one's not admissible, so anyway, we're done. Okay, great. Let's go out to n plus 5, where we have square 5 iota n. Now, there should be square 4, square 1. Oh, but square 1 is 0. There should be square 3, square 2. Oh, but square 3, square 2 is just 0 on its own. So that's not interesting. And then we're down to square 2, square 3. That's not admissible. Okay, great. So that's the cohomology of their base, at least for a little while. Of course, it continues on. Now, the cohomology of the fiber starts in degree n plus 1 with our fundamental class. And now this is a KZ mod 2 for n plus 1. So, sorry, not the number 4. KZ mod 2, comma, n plus 1. So this just looks like the student algebra. No funniness about the square 1 being 0, right? Now I've got square 1 iota n plus 1. And really, this should just look like the Steenrod algebra up to degree 2n, but I can make my n large enough that I can get any squares I want. So that was in degree n plus 2. In n plus 3, we've got square 2 iota n plus 1. Then in degree n plus 4, we've got square 3 iota n plus 1. Now we do have square 2, square 1, because square 1 is not 0 over here. In degree n plus 5, we've got square 4 iota n plus 1, square 3, square 1, iota n plus 1, and then the next would be square 2, square 2. That's not admissible, and it's actually the same thing as square 3, square 1. So that was this relation right here at the top. Okay, so this is what we have, and I'm realizing I don't have room to write the things I want to write and also keep the addend relations here. So I'm going to hope that you've sort of written those off to the side in your notes, and let's continue on. So we just verified really explicitly that indeed tau of iota n plus 1 is square root 2 iota n, in a sense, by construction, right? So that tells me that that tau, my transgression, does take iota n plus 1 to square root 2 iota n. And then just as we saw in the last video, that tells us that if we wanted to look at square 1 iota n plus 1, well, square 1 commutes with the transgression, so that's square 1 of tau of iota n plus 1, and so that's square 1 square 2 iota n, and then that's square 3 iota n. Remember, just because we're writing things as admissibles, that's how we're going to see it over here. And so yes, that one transgresses to square 3 iota n. Okay, we'll just keep going and try computing what the transgression does to a bunch of these. So the next one's square 2 iota n plus 1. Well, I can pull the square 2 out and then get square 2 iota n. Square 2, that was one of our Dem relations. And that's square 3 square 1. Okay, so square 3 square 1. Oh, but now I've got square 1 iota n, which is 0. So that one's just 0. Okay, so that tells me that square 2 iota n is in the kernel of the transgression. And remember, there won't be any polynomial or sort of tensor products stuff to hit. In fact, the fact that the transgression commutes with this says that's it can't have died earlier. So in any case, that's going to be in the kernel, and live to the cohomology of x1. Okay, let's look at, this is all getting a little tight. Let's look at tau of square 3 iota n plus 1. Well, I can pull the square 3 out, and then that's square 3 square 2 iota n. And one of our Dem relations tells us that square 3 square 2 is 0. So that's 0. All right, and that tells us, I guess, that this one is in the kernel. Then I can look at square 2 square 1 iota n plus 1. That's something else that's in that degree, and this is not going to fit here. So I'm looking right here and asking if that hits anything. But let me move this computation down. So again, the Steiner-Raud squares come out, so that's square 2 square 1, and now square 2 on iota n. And now that doesn't look like an admissible sequence, so I want to do some Dem relations, right? And square 1 square 2 is square 3. So that's square 2 square 3 iota n. And there was an Dem relation there for square 2 square 3. That's square 5 plus square 4 square 1. Okay, so I really have all of that applied to iota n. But remember, square 1 on iota n is going to be 0, so that term's going to go away. And I'll just have square 5 iota n. Let me just say, etc. So let's not keep computing. But if you did, you would find that there are things where you do hit sums like this and they don't go away. So things can be a little bit more complicated, but it works out kind of nicely here in the beginning. We just learned that square 2 square 1 iota n comes and hits square iota n plus 1 comes and hits square 5 iota n. Okay, I think you're maybe already starting to see that this is really the kind of computation you need to sit down and do for yourself. And so that's part of why I'm not going to take this much further, but I wanted to give you kind of the tools, at least to get started, or to sit down and read this part of Mosher and Tangora if you're interested. Let me point out that already from this, that nothing can come and hit square 4 iota n. So that's going to be something in the co-kernel of the transgression. And that's going to be something that lives to the E infinity page, and so lives to the cohomology of x1, the thing we're converging to. Okay, and so already we see that we do know the cohomology of x1, at least in a range. So we're going to want to look at total degrees, and we see, oh yeah, in total degree n, we've just got this 1 iota n. Then we've got nothing in total degree n plus 1, nothing in total degree n plus 2. We do have something in total degree n plus 3, and 2 things in total degree n plus 4. So let me write that down. Okay, so far we see that hn of x1, that was z mod 2, that's our iota n, gives rise to that one. Hn plus 1, as we said in the last video, and we just saw again, oops, is 0. Hn plus 2 is also 0. I think we knew that, but now we've also computed that Hn plus 3 is a z mod 2. And that z mod 2, maybe we'll name the generator here alpha. That alpha, that came from what? So this is in degree n plus 3. Oh, and I've written over it, but that's square 2 iota n plus 1. So this generator alpha really kind of comes from square 2 iota n plus 1. And then you may remember we saw 2 things in degree n plus 4. So that's z mod 2 direct sum, z mod 2. And those things came from square 4 iota n, that was something from the base, and square 3 iota n plus 1, that was something in the fiber, and of course square 1, well, I don't know how to write this, square 1, square 2 is square 3, so there's a square 1 connection here, in a sense. And in fact, we can make this really precise. There's technically some indeterminacy here, the way that we've done this. Really, we have kind of an extension problem of the cohomology as a module over the Steenrod algebra. And so it's possible that square 1, I should have labeled that, that was my square 1, my Bockstein. It's possible that square 1 just hits this, or it's possible that it hits the sum of these two classes. And from what we've done so far, we can't actually tell, but it turns out it doesn't really matter. So we'll just say there's something that's square 1 alpha, and there's something else. Okay, so in any case, maybe let me say modulo extension problems that are not such a big deal here. And of course, we could continue this computation. That's as far as we went. We didn't even determine. We saw that something in degree n plus 5 was hit. Let's scroll back up. So this square 5 iota n was hit, but I'd have to keep going to figure out whether these support differentials and so on. So in the interest of not completely losing you, let me stop there. But let me point out kind of what we've got so far. So this space x1, this was supposed to, in a way, approximate our Sn, right? And its cohomology looks like Sn in a range, but then it gets messed up. So this Hn plus 3, this is really our first obstruction to this looking like the cohomology of Sn. Okay. And so the game that we play is essentially to kill off these obstructions. And ultimately, at some point, we'll have to kill off these higher obstructions too, but let's just deal with this first one. So the game is to kill alpha. And how do we do that? Well, this alpha is something in hn plus 3 of x1. So how do we kill a cohomology class? Well, we play that same game that we did earlier. We say, oh, alpha can be witnessed as a map from x1 to, I guess, kz mod 2 n plus 3. Right? It's something in hn plus 3 of x1 in mod 2 coefficients. So there's a map that witnesses that. And there's a loop path fibration over here. Now the fiber will look like kz mod 2 n plus 2. And I can take the pullback, and that's what I'll call x2. And now it has the same fiber, so we get another fibration with the same fiber. Oops. Okay, and now we'll look at this fibration that we've just created and run the cohomology Sayre spectral sequence, mod 2 of course. And this x2 will be a better approximation. So the claim is that this will exactly kill off this class alpha. So let's see how that goes. Well, we've got our Sayre spectral sequence, the cohomology of the base, which we only know in a range, in a pretty small range right now, that's x1. Then the cohomology of the fiber, that's kz mod 2 n plus 2. Okay, and so we've got our 1 there. This started in degree n. I'm going to call this iota n just because that's what it came from. Remember, this hn of x1 was a z mod 2, and that showed up there because of iota n, so I'll call it that, even though it's a little bit of a misnomer. Then in degree n plus 1 we had 0. In degree n plus 2 we had 0. In degree n plus 3 we have this alpha. And in degree n plus 4 we've got two z mod 2s. So one of them is square 1 on alpha, and the other one is square 4 iota n. And notice I'm being kind of vague about whether that square 1 alpha really is square 3 iota n plus 1 coming from that, or if it's the sum of those. I don't really care. But then, okay, over here, in degree n plus 1, now this is an honest cohomology of an Eilenberg-MacLane space. Whoops, that's not where that goes. That goes in degree n plus 2, and should be named iota n plus 2. Okay, well, then of course, in n plus 3, we've got square 1 iota n plus 2, square 2 iota n plus 2, and so on. So that's entire Steenrod algebra. And we haven't even worked out this part, but of course it continues. And now, again, that by construction, having this map alpha here, we can go through the same argument to see that that tells us that this iota n plus 2 transgresses. Okay, so tau of iota n plus 2 is alpha. Oh, sorry, maybe I should remind you this is all converging to the cohomology of x2, mod 2 coefficients. Okay, so this is really by construction. And now you know what I mean by that. Run through that same argument again. Now tau commutes with the square, so I can look at square 1 on this, and I should get square 1 on alpha. Okay, and so this thing will come and hit here. And it turns out that nothing, well, there's nothing else there, I guess, in degree n plus 3, and so nothing hits this square 4 iota n, so that's going to live. And so at the next stage, that's something that we would want to kill off. But anyway, let me stop there in that computation because I just want to give you the idea. And let's see what we've now learned from x2. Well, looking at this computation, we know that hn plus 1 of x2 is the same as hn plus 2 of x2 is the same as hn plus 3 of x2 is 0, right? But of course, we just saw hn plus 4 of x2 is not 0. Oh, and maybe I should have said hn of x2 is z mod 2. So going back up to our x1, we had z mod 2, 0, 0, and then something. And now we've just extended that a little bit further. We've got z mod 2, 0, 0, 0, and then something. Okay, so this is a closer approximation to the cohomology of Sn. Now, how does that even really help us? Well, we'll have to look at the Long-Zach sequence in homotopy to make use of this. Okay, and in fact, maybe really 2 Long-Zach sequences in homotopy. So let me first look at the fibration that we had before involving x1. I didn't need to say this at the time, and so I didn't bother, but I'll need it now. Okay, so that was what our fibration looks like with x1 as the total space. And notice that we'll only have interesting homotopy groups in degree n plus 1 here and degree n here. And so away from that, I've got a whole bunch of zeros. Okay, so in particular, running that Long-Zach sequence is going to tell me that pi n plus 2 of x1 is the same as pi n plus 1. Sorry. It's the same as pi n plus 3 of x1 is 0. Pi n plus 1 was z mod 2, you may recall. Maybe as long as I'm saying it, let's write it down. That just came from matching this spot. Okay, and that was how we saw our first stable homotopy group was z mod 2 because we were able to compare that to Sn. All right, now, so that's something from our old fibration. From this new fibration, what do we have? Well, our new fibration is gone off the page. There we go, kz mod 2 n plus 2 to x2 to x1. Okay, so in this new fibration, if we run the Long-Zach sequence, then in particular we'll have, say we go to pi n plus 3 of x1. It's going to map to pi n plus 2. That's the interesting spot of the fiber. Maps to pi n plus 2 of x2. Maps to pi n plus 2 of x1. And so on, but we just noticed pi n plus 2. Oh, sorry. Yes, pi n plus 2 of x1. I'm using parentheses half the time and not consistently. Okay, so pi n plus 2 of x1 we just saw was 0. And of course, pi n plus 3 of x1 we also just saw was 0, so that makes this an isomorphism. Here this is a z mod 2 basically by definition, and so this is a z mod 2. All right, and just like in the end of the last video, that tells us about the homotopy groups, or at least the 2 component of Sn. So let's just let's sort of collect up all this information. So pi n x2 is the same as pi n of x1. They agree there. Notice that that I'll be trapped between zeros because this is only interesting in degree n plus 2. So those are the same. And that was a z mod 2. I guess I didn't write that down from... Oh, sorry, that's a z. That comes from here, right? And then pi n plus 1 of x2 is also the same as pi n plus 1 of x1. That one's a z mod 2. We did just remind ourselves of that one. Okay, and pi n plus 2 of x2, we've now just learned is a z mod 2. Okay, so in exactly the same way as before, remember we had a map from Sn and we got a map to the total space that lifted it and so on, the same argument. This implies the two component maybe I should go back before I complete this sentence. So the cohomology of this thing looks like the cohomology of Sn for a little while. And so the two component of the homotopy of Sn will agree with the two component of the homotopy of x2 for a while, and it's precisely in these degrees. And so this last one tells us that the two component of pi n plus 2 of Sn, maybe let's write that here, which is pi 2 stable, as long as we take our n to be pretty large, is this z mod 2. And that's coming from this z mod 2 here. Okay, so we now have a new stable homotopy group of spheres. Notice that we only know the two component. I believe in this particular case, you can check at the odd primes, playing a kind of similar game, that in fact, though there you'll need the odd prime, Steenrod algebra, that kind of stuff. But in fact, I think this is actually just a z mod 2, though I can't remember off the top of my head. But continuing in this way, and in fact they go through this in Moser and Tangora chapter 12, so that's what I'm following here, then we can get the two component of the stable homotopy groups. So they can get as far as, let me remind you, this is just the two component. So they get as far as the 7th stable stem. And okay, we already knew the 0th stable stem was z. The first we computed last time, the two component, and even before that we knew the whole thing was z mod 2. We just learned this z mod 2 here for pi 2 stable. If we kept going, we could get a z mod 8 for pi 3 stable. Now that's going to require some Bachsteins, right, to recognize that it's not just z mod 2s, because we were doing the whole spectral sequence in mod 2 coefficients. So there's some Bachstein arguments that go into that. You can also get that pi 4 is 0, 5 is 0, 6 is z mod 2, and 7 is z mod, I have written down 16, but now I'm questioning it. Yeah, I think this is z mod 16, but if you take into account odd primes, there's more there. And in fact, I think that's also true already here at this z mod 8. So I think actually the whole thing is z mod 24 for pi 3 stable. In any case, the point is you can continue this computation on quite a bit further. And I just want to finish off with one kind of neat observation here, which is that we can actually learn from this. If we had extended this all the way to get this 0 here for pi 4 stable, we learn as a corollary that eta, the Hopf map, is nilpotent. So how do we see that? Well, remember eta lives here in pi 1 stable. So eta is in pi 1 stable. Eta squared meaning composed with the suspension of eta. This is going to be in pi 2 stable. And then eta cubed is something in pi 3 stable, but eta to the fourth is something in pi 4 stable. And this argument, if we carried it on, would show us that the 2 component at least is 0. Again, I believe that actually the whole thing is 0, just like I believe the whole thing of pi 2 stable is Z mod 2. But in any case, the 2 component is 0, and 2 times eta is 0. So, eta was going to live in the 2 component. All the powers of eta are going to live in the 2 component. So, in fact, that does tell us that eta to the fourth is 0. Okay, so that doesn't actually tell us that eta cubed is not, but at least eta to the fourth is 0. And it turns out that eta cubed is not 0, but indeed eta is nilpotent. And one of the kind of neat things that happens when you go and study, say, equivariant homotopy theory or motivic homotopy theory is that suddenly eta, this Hopf map, is no longer nilpotent. And so you get a whole explosion in the homotopy groups of spheres and some neat phenomena. But in any case, this video has now gotten quite long, so let me stop there. But what have we done? Just to round it out, we explicitly computed the 2 component of pi 2 stable, and here we saw that we got a Z mod 2. And we could continue this argument with a little bit of some subtleties, a little bit of extra stuff that's described in Mosher and Tangora, and we'd be able to get the 2 component of pi 3, Z mod 8, the 2 component of pi 4 is 0, and so on. And so that tells us that eta is nilpotent. And I think they compute this out to pi 7. I can't remember if that's really as far as you can go or not, but you can't just power through and go forever. At some point, you will land on a differential that you can't decide in this way. And so then you need to reach for some other methods. And that's where things like the atom spectral sequence come into play. But okay, let me stop there.